Good.
Now it's here. So now let
Yeah.
let me show. Now we will have talk of Daniel Sethio from the Sweden University, Uppsala University, revealing strong C4E halogen bonding solution. Uh, so it's a pleasure to have your talk, and now it's up to you. We have
Okay.
initiated. So it's up to you then.
Okay. Thank you. Can you hear me?
Yes, it's
Can you
okay.
see also my slide?
Yeah.
Okay. Okay. Good morning, everyone. Bom dia. So first of all, I would like to thank the organizer for giving me opportunity to participate in SIDMOL 2022. Unfortunately, I couldn't come in person and visit Brazil this year. So my name is Daniel Sethio. I'm a researcher at Uppsala University. Today, I would like to present about my work about revealing the strong three-center for electron halogen bond in solution. So non-covalent interaction has received a lot of attention due to their importance in many fields such as physics, chemistry, biology, and material science. It is believed that the chemistry of the present century is more likely to be the chemistry of non-covalent interaction, while the chemistry of the last century they believe is mostly the chemistry of covalent bonding. The non-covalent interaction play many important role in determining the state of the material and playing important role in drug-protein interaction and also protein-protein interaction and stabilizing the molecular structure. The term non-covalent interaction referring to the interaction between molecules or atoms which are not covalently bonded. In terms of energy, the non-covalent interaction typically have interaction energy lower than 300 kJ per mole, while typical covalent interaction is higher than 300 kJ per mole. So the origin of non-covalent interaction can be explained by the charge transfer. The charge transfer from the lone pair of the Lewis base to the sigma star of the halogen atom is stabilizing this interaction. The other that the origin of non-covalent interaction can also be explained by electrostatic potential. So due to the anisotropy electron distribution of electron density, there is a region where there's a region where diminishing electron density, and this region possesses a positive electrostatic potential. If this positive electrostatic potential uh, exists in the elongation of sigma bond, it's called sigma hole, and in the pi bond, it's called pi hole. Recently, there are many well-known non-covalent interactions. For example, non-covalent interaction group 13 is called trial bond. For group 14 tetrabond, for group 15 pnicogen bond, for group 16 chalcogen bond, halogen bond for group 17, and aerogen bond for group 18. In today's presentation, I would like to focus on halogen bond interaction, which is in the group 17. The halogen bonding is defined as a net interactive interaction between electrophilic region associated with a halogen atom with a nucleophilic region associated with a usually Lewis space. A moiety of electrophilic region is called halogen bond donor, and then the moiety with a nucleophilic region is called halogen bond acceptor. The interaction energy of typical halogen bond are relatively weak. Its range between 0 to 44 kilojoule per mole. So, how to build the stronger halogen bond? So, one strategy is by increasing the polarity from fluorine to iodine. The fluorine is the weakest halogen bond donor, and iodine is the strongest halogen bond donor. And the second strategy is by uh, substituting the side group attaching to halogen bond donor with more electron withdrawing group, and also by replacing the side group in the halogen bond acceptor with electron donating group. The halogen bond donor even can have more stronger uh, interaction by changing to the electron deficient halogen ions. This halogen can interact with two Lewis base, forming three center for electron bond. It typically has a pi hole rather than a sigma hole. And then typically this distance is shorter compared to the normal halogen bond, and the ratio is typically 0.7%, like 70% shorter than van der Waals radius between the sum of the nitrogen and the halogen. And the interaction energy is close to 100 kilojoule per mole. So in the first study, we would like to benchmark the DFT methods for the description of NMR chemical shift. The aim of this study is to find the best suitable DFT functional which can describe the NMR chemical shift of three center for electron halogen bond complexes. So here we use 170 experimental proton, carbon, and nitrogen NMR chemical shift to benchmark the DFT functional. And the question why we need a new benchmark for this. The reason is because this complex is on very unique three center for electron bond, and it has typically strong hydrogen bond, which is higher than 50 kilojoule per mole for each bond, and the bond is shorter than usual halogen bond. So in this justification that we think that we need more benchmark for this typical strong halogen bond. This figure shows the normalized root mean square deviation from experimental NMR chemical shift for proton, carbon, and nitrogen atoms. As we can see here, that the nitrogens have the largest deviation from the experimental chemical shift, and followed by carbon and proton. So we can see here there are 7 advisable reasonable functional, such as MO6, B3LIP, ChemB3LIP, LC-TPSS, LC omega PBE, and omega B97XD. To use the pure local functional such as MO6L is not advisable. And then we play also with different basis set. So we found that triple zeta basis set give reasonable results, whereas different flavors from Popple, Ulrich, and Dunning basis set has smaller influence. So in general, the combination between MO6 with Dunning triple zeta basis set is give the most accurate results. So for the second study, we are curious on this paper, on the previous paper. They claiming that there's interaction between silver plus and iodine plus, and and we want to reinvestigate what was happening, whether this interaction is possible or not. So in the experimental part, they are managed to crystallize these complexes. They have two different phases, one with 3.53 Armstrong and the other one with 3.52 Armstrong, the distance between silver and iodine. And they also performing the NMR chemical shift, and they observe the coordination shift between nitrogen here is is shifted when they change different side group. They also performing DFT calculation using experimental crystal lattice. So they don't optimize the complexes. They use the geometry from the X-ray structure directly. So in the Q-time, they observe there's a bond path with bond critical point, and also reduced density gradient. They observe that there is should be a weak interaction between silver and iodine. And also from NBO analysis, there is a charge transfer from 5p of iodine to the 5p of silver, which stabilizing this interaction. However, in the supporting information, they mentioned that the interaction between silver and iodine is basically repulsive. And from the energy decomposition analysis also is more or less repulsive. The charges, both of them are positive, and they claim the stabilization of these complexes mostly from pi-pi interaction. So it's come from our question, is there really any interaction between silver and iodine if this complex is dissolved in the solution? So we reinvestigate using the same level of theory. So we use MO6 2x and also R-Rich triple zeta basis set. And then we re-optimize the structure using PCM, and we observe there is no imaginary frequency, meaning that this structure are in the minimum energy surface. We also observe that there is a bond critical point between silver and iodine, and also a bond path. The reduced density gradient also saw a weak interaction between silver and iodine, and also from pi-pi interaction in this case. We also try different non-covariant interaction tools such as independent gradient models, density overlap region indicator, van der Waals surface, and interaction region indicator, IRI. And all of them show that there is interaction between silver and iodine in these complexes. And however, when the experimentally was performed in our lab, we couldn't observe any silver and iodine interaction in the solution. Why? So I will walk through how the interaction energy was calculated. So the interaction energy was calculated by calculating the total energy of the complexes minus the total energy of isolated iodine and isolated silver complex in their optimized geometry. So we don't optimize, we keep the geometry of these complexes as they are optimized in the dimer. Here is the results that all the methods, including MP2 and couple cluster, they show that this interaction energy is stabilizing. So the DLPN or couple cluster give the interaction energy minus 8 kilocalorie per mole. However, this interaction energy is only taking into account the electronic effect at 0 K. So if we include the vibrational, the rotational, and translational correction into the electron energy, we will get the internal energy, which will destabilize by 1 to 2 kcal per mole. And by including the thermal correction, it will further destabilize by 1 to 2 kcal per mole. And by including the entropy correction, it will more destabilize by more or less 7 kcal per mole. So in total, that the isolated complexes of silver and iodine complex is more preferred in solution compared to the dimer. They are differ by more or less like 9 kcal per mole, and the Boltzmann distribution of this in solution is they are preferred mostly 99.99% as isolated in the solution. So what stabilizes the complex if the complex had formed? So we follow the same procedure like in the previous paper. So we take the dimer and then we remove one of the complexes, for example, iodine in this case, and we kept the geometry and then calculate the interaction of the G in this case. So as we can see here that the dominant stabilizing factor in this complex is mostly from pi-pi interaction. So in conclusion, in solid state, this complex is exists due to the stabilization come from crystal packing. While in the solution, they prefer in the isolated fragment compared to the complex. And then the main stabilization of this complex mostly from pi-pi interaction, not from silver iodine interaction. And then the next study is about detecting weak halogen bonding in solution. So as we know, detecting weak halogen bonding in solution is very difficult. It's very challenging, and there are very limited experimental technique to probe this. For example, we can use vibrational spectroscopy. Only can be used in solid or in the gas phase. While NMR chemical shift of this weak halogen bond only give a small NMR chemical shift, which is hardly to detect. So the aim of this study is to propose a new toolbox to probe this weak halogen bonding. So we propose using scalar coupling constant, using in the 31 complexes of halogen bond, weak halogen bond complexes consisting of aromatic and aliphatic halogen bond donor. In the aromatic, we have as a base, we have pyridine, amine, and N oxide or carbonyl here in this case. And we propose to use the scalar coupling constant for example, in the aromatic, we use the scalar coupling constant in the ortho, meta, and para position. And then in the aliphatic, we propose using alpha, beta, and ipso position. As we can see here, that the scalar coupling constant versus the strength of the halogen bond donor is correlate well each other. It's correlate each other. So and then in the ortho position is highly influenced compared to the para and the meta. The same for the aliphatic that alpha position have a larger magnitude compared to the beta and very small compared to the ipso position. In the calculation, we use geometry topology and scalar coupling constant calculation. So in the geometry, we use bond length, atomic charge, hybridization, binding energy as a descriptor. And for the topology, we perform Q-time analysis to get the electron density and energy density. The energy density is used to classify the covalency of the bond. If it is negative, is we can classify it as a covalent bonding, while if it is the energy density at bond critical point is positive, we can classify it as electrostatic or non-covalent reaction. We also perform decomposition of scalar coupling constant into four Ramsey components into Fermi contacts, which are dominating by the S character, and non-contact component is mostly dominated by the P character, spin dipolar mostly dominated by the P type of the pi orbital, while the paramagnetic spin-orbit coupling mostly dominated of P sigma and the P pi orbital. And the dimagnetic spin-orbit coupling is mostly dominated by the ring current. Here we observe that the scalar coupling constant is correlating well with the hybridization of the iodine atoms and also with the strength of the halogen interaction, as we can see from the electron density at bond critical point. So in conclusion, the scalar coupling constant can be used to detect the weak halogen bond in solution. For the aromatic system, the scalar coupling constant of ortho is larger than para, and the weakest is meta. And for the aliphatic system, the order of the scalar coupling constant is alpha is larger than beta and larger than ipso. And we know that the mechanism how this halogen bonding transfer to the alpha beta and ortho meta and para and alpha beta and ipso is due to the Fermi contacts. So the Fermi contact is the dominant contribution of the total scalar coupling constant. So this mechanism is mostly through bond mechanism using sigma type character. And as previously also observed for hydrogen bond, the scalar coupling constant have linear correlation with hybridization character of the halogen bond donor. And the scalar coupling constant correlate well with electron density of the CF bond at bond critical point, which indicating as the strength of halogen bond donor. And the last study, we would like to use this halogen bond donor in the activation of gold catalysis. So as we know that the gold catalyst has become a powerful tool for synthetic organic molecules. However, the initial gold catalyst, which containing chlorine, this catalyst is inactive. And to be inactive, we need to subtract this chloride, which mostly people using silver to subtract this chloride to make this gold catalyst active. So in this present study, we suggest to use this halogen bond donor to subtract this chlorine. And by using this, we believe that this is more sustainable compared to the silver.
Okay.
Okay. Can we talk later?
Yes. Sure.
So here, in this case, we use cyclopropionation reaction as a reaction test for gold catalysis. So we use 6 different gold catalysts and 5 different halogen bond donor. In the experiment, here we perform the the relative rate of different gold catalyst and activator. And in the computational study, we use different descriptor to describe what was happening in the experiment. And the rate of detection are proportional to the strength of halogen bond donor. And we also we will also propose the reaction mechanism at a B3 with triple zeta basis set quality. And we can observe that this halogen abstraction is the rate determining step for this reaction to occur. And this halogen bond donor give comparable performance compared to this state-of-the-art sodium BRF. As we can see here, the halogen bond donor activator perform comparable to this performance. So the take-home message, I hope I can convince you that NMR spectroscopy is a powerful spectroscopic technique to detect halogen bond in solution. So we can use NMR chemical sieve, proton, carbon, and nitrogen NMR chemical sieve. And in this case, we also propose to use the scalar capping constant as a new toolbox for characterizing weak halogen bond in solution. And second, the halogen bond donor can be used as a new tools in catalysis to activate, for example, in gold catalysis. So I would like to thank the funding agency and also supervisor, uh, collaborator, and also the organizer, Professor Zhao, for giving me opportunity to give presentation in this conference. And thank you very much for your attention. Muito obrigado.
Can you hear?
Yeah, I can hear you.
Yes. Oh, okay. I will see if there is some question for your talk. Wait a moment. Hold on.
Mhm.
This one? Questões?
Sometimes your sound is off and off, on and off.
No. Well, I have a question here. I have a
Yeah.
question. How about the local modes? Have you used it to the for this interesting cation interaction?
Yeah. So I have used a local mode, for example, to see whether this complex is exists in solution.
Yeah,
And
yeah.
the local mode also show that there is a possibility of this silver and iodide interaction, a weak one.
But what about? I understand that there is a pi interaction here,
Yeah, correct.
and the local mode shows this interaction.
Yes, yeah. Local mode also show that the pi-pi interaction is larger compared to the silver iodine interaction.
Okay,
Mhm.
okay. Hold on. Any questions? No questions. You Vocês podem fazer em português, eu faço a tradução para ele. No? Okay. And well, you have studied also the important, the relevance of the solvent model here.
Mm-hmm.
Yes, but I remember that you have used the PCM model.
Correct. Yeah.
Yes. Well, yes. This cation-cation interaction,
Mm-hmm.
it's another, the last talk for your talk here, we was about cation-cation interaction.
Yeah.
Andres Velasco from Colombia was talking about this interaction using
Mm-hmm.
a positron bonding this cation-cation, and this positron he shows that this positron makes this interaction more strong.
Okay.
It's interesting because I don't know if he will talk about this again.
Okay.
Okay, Daniel,
Yeah.
I like to again. Have you heard the people here or no? No,
No.
no. Okay.
No.
Well,
Yeah.
thanks again for
Yeah.
your
Thank
talk.
you. Thank you,
And
Professor Zhao.
okay,
Yeah.
so let's. Have you here now?
Yeah.
Have you here?
I
Yeah.
have it.
Okay. Yeah.
Yeah.
Thanks.
Thank you.
So you finish our transmission. Okay.
Yeah. Bye.